Our today's discussion is on simulation of a single-stage grid-connected three-phase solar inverter using MATLAB. This is the basic schematic of a single-stage grid-connected three-phase solar inverter. Here the output of the solar panel is directly connected to the inverter input. LCL filter is used for filtering out the harmonics in the grid current. Now I will give the specification of the complete system. Open circuit voltage of the PV array is 907.5. Operating voltage range will be between 700 to 900. The switching frequency of the inverter is 10 kHz. The value of the filter inductor is 500 microhenry, and the filter capacitor is 100 microfarad. The grid voltage is 400 volt line-to-line RMS, at 50 Hz. The rated power of the system is 100 kW. This is the complete control algorithm for a single-stage three-phase grid-connected inverter. Most of the things are similar to what we explained in the two-stage system. Only a few differences are there, that I will tell you now. In the two-stage system, the output of MPPT is used to generate the PWM signals for the boost converter. But here, we use the MPPT converter output as the reference for DC bus voltage controller. Another difference is that here we need to add a feed-forward term to the output of DC bus controller. The value of feed-forward term is given by 2 by 3 into VPV divided by VD. Everything else in the controller remains the same. Now we open the MATLAB and start doing simulation. First we add the solar PV array. Set the number of series and parallel strings. Now let's plot the VI curve of the array. This is the MPP voltage and maximum power for 1000 irradiation. This is the same values for 500 irradiation. And this is for 100 irradiation. This is the open circuit voltage. And this will be the MPPT operating range. Add a constant block. Set the irradiance 1000. Set the temperature 25 degree. Add a bus selector. Select VPV and IPV. Add a unit delay block. Set its sample time 1e raised to -4. This is the MPPT block, which we have already discussed in the last couple of videos. So I just copied this block from there. Now we need to do some modification in this, according to the simulation. Change Vref max to 907.5, that is the VOC of the array. And change Vref init to 750. Add a go-to block. Name the MPPT output as VDC ref. Now we make the three-phase bridge. First add an IGBT. Add an input signal port, and connect to each gate terminal. Name them from PWM1 to PWM6. Add a series RLC branch. This is the input bus capacitor, and give it a value 1000 microfarad. Add a connection port. Make port location left. And name it as VDC+. And name this one as VDC-. Name this as VR. And make port location right. Name this one VY. And name this as VB. Now create subsystem from the selection. Delete all the ports and signals. Connect the inverter into the solar PV array. Add a from block. Connect this to each PWM. Name all the signals from PWM 1 to 6. Now we need to label PV voltage and current. For that, add a go-to block. Give name VPV. And this one, IPV. Add a 3-phase VI measurement block to measure the inverter current. Label the current as IABC. Add a series RLC branch. This is the grid side filter inductor, and set its value 500 microhenry. This is the filter capacitor and set its value 100 microfarad. Add a three-phase VI measurement block. This block measures the grid voltage and current. Label the voltage as VABC and current as IABC1. Flip the block before making the connection. Add a three-phase source. Flip this block also. Set the voltage 400 volt and frequency 50 Hz. Now we make the voltage and current transformation blocks. Add a from block. Name it VABC. Add ABC to alpha beta transformation block. Add alpha beta to DQ transformation block. Add another from block. Name it as omega t, which is the output of PLL. Add a go to block. Name it alpha beta. Add a demux. Add a go to block. Name the output of voltage transformation block as VD and VQ. Now similarly add current transformation blocks. Name the current transformation block output as ID and IQ. Now connect PLL. For that we need alpha beta voltage. Add alpha beta to DQ block. Add a sum block. Make the sign minus plus. Add a constant block, and give it value 0. Add APID controller. Set its KP and KI values. Add an integrator. Name PLL output as omega t. Now start connecting voltage and current controller blocks. Adder from block. Name it as VDC ref, that is the output of MPPT. Add a sum block. Mark its sign plus minus. Add another from block. Name it as VPV. Add APID controller. Set its KP and KI values. Add another sum block. Here we add the feed forward term. Add a product block. Adder from block. Name it VD. Add a gain block. Give it a value 2/3. Add another product block. Adder from block. Name it IPV. Now we start connecting the D-axis current controller blocks. Adder from block. Name it ID. Add another PID controller. Set its KP and KI values. Add another sum block. Add a gain block. Give its value 2 into pi into 50 into 1000 e raised to minus 6. Adder from block. Name it VD. Add a gain block. Give it value 2. Add a product block. Now we start making Q-axis current controller. Add a constant block. Set IQ reference 0. Add a sum block. Add APID controller. Set its KP and KI values. Add another sum block. Change its sign to plus minus. Add a gain block. Give its value 2 into pi into 50 into 1000 e raised to minus 6. Add another sum block. Add a gain block. Give it value 2. Add a mux. Add a DQ to ABC transformation block. Add a from block. Name it omega t. Now we connect the PWM generation blocks. Add an in port. Name it vref. Add a demux. Add a relational operator. Change the operator. Add a repeating sequence. Here we set the switching frequency. I am using 10 kHz triangular carrier signal for switching. Add a logical operator. Make the operator not. Add an output signal. Name it PWM1. Create subsystem. Delete all signals. Add a go-to block. Name it PWM1. Now add a scope. Add grid voltage and current to the scope. Add another scope. Add PV voltage to the scope. Add a power measurement block. This block measures the power fed to the grid. Add a power guy block. Open model configuration parameters. Select fixed step type. Select solver ODE8. Give step size 1e raised to -7. Open power guy. Set simulation discrete and step size 1e raised to -7. And finally, set simulation time 1 second. I made a mistake here, need to change the sign of the sum block. This filter connection is also wrong, so we'll correct that also. Now run the simulation. Let's open the scope to see the voltage and current. Here you can see the power. We have encountered an error here. This is a very common error that mostly appears when we simulate the PV array circuits. Now I will show you how to get rid of this error. For that, open the inverter sub-circuit block. I have used a 1000 microfarad capacitor at the input. Now I will split this into two 500 microfarad capacitors. Now run the simulation again. Open the scope to see the voltage and current. You can see that grid current and power has reached the MPPT point, corresponding to 1000 watt per meter square irradiation. Now we'll try to change the irradiation. I will make it 500. Grid current and power now has moved to the new MPPT point. Now I will try 200. Since I reduced the irradiation, grid current is coming down. Now I will change to 750. Since we increased the irradiation, current started going up. Now we make it back to 1000. Now current has reached back to the original value. I will also show you how the PV voltage is varying. So this is how PV voltage is varying with MPPT. This is the end of this presentation. Thanks for watching.